Hello everyone, welcome back to ECE100 class 17. We're going to talk about capacitors. We talked about resistor, we talked about diodes and LEDs. Now we're going to talk about capacitors. So let's get started here. So in a passive circuit, we have three elements. We have resistors, then we have capacitor we're going to talk about today, and inductor we're going to talk about in the next class. So let's review what we know about the resistor. So resistor, we know that this is a linear device. It obeys Ohm's law. All right, and also resistor does not store any energy. It dissipates energy but does not store. So resistor dissipates energy. Dissipates energy. All right, so that's what we know about resistor. All right, so let's see what is a capacitor. So now there are two plates over here. In the middle here is vacuum or air or any other dielectric materials. So this is a non-conductive dielectric media. That means your charge cannot travel through that gap, dielectric medium. All right. So if we turn, let's say you have a 12 volts, for example, here. So if I close the switch, what will happen that all the positive charge will come across these plates over here, and all the negative charge will come across these plates here. So that means across these two plates we have the same 12 volts, right? So that means the capacity over here is that these two plates can hold the 12 volts out there. All right, so and what does means? What does that means? All right, so you also know that your charge is basically like how much capacity these two plates has to hold charges. That's what we're gonna go into. All right, so we can also measure capacitance using your fluid 117. If you look at here, there is a capacitive sign over here, so you need to bring that knob to that sign. And also this is yellow color, so you have to press the yellow button here. Then you can measure capacitance. Capacitance, there are two types. One is polarized, one is non-polarized. This is the polarized one. They have a polarity here. And this is the non-polarized one. It doesn't have any polarity. And the unit for capacitance is Faraday, which is coulomb per volts. So capacitance is coulomb per volts. So what is the definition of capacitance? Capacitance is the capacity to hold charges per unit voltage. So how much charge you can hold by per unit voltage, that's the capacitance. That means C is Q over V, right? So how much volts, how much charges here, how much charges you can hold per unit voltage. So capacity to hold charges per unit volts, right? So that is the capacitance. So if I go back to the last slide, that's what I'm saying over here. So there's a 12 volts over here. If this 12 volts, if we hold, let's say 100 coulombs of charge, then your capacity would be 100 coulomb over 12 volts. That is 100 over 12 is 8. So your C would be 8.33 Faraday. right? That's your capacitance for that plate. So how much charge you can hold per unit volts, that's your capacitance. That's what you have C equal to Q over V. And that's a coulomb over volts, all right? And capacitance, normally we have picofarad, nanofarad, microfarad, or millifarad is too big. In the lab, we normally use these two, nanofarad and microfarad of capacitance. These are different shape and size of capacitance here. You will see them in your lab when you use them to build circuits. So as I say, there are two different types. One is polarized, normally electrolytic capacitors, they're polarized, and ceramic capacitors, they're not polarized. So this one symbol would be your polarity over here, is positive, right? This one is no polarity here, so that is your ceramic capacitor, okay? This is the positive side here, negative side here, that's the polarized capacitor, okay? And when you see a polarized capacitor, there are two ways to know it. One is the longer lag is your positive, shorter lag is a negative. If you cut them equally, then there is a sign over here that show you your negative sign on that side for the negative side of the capacitor. And also over here, if a cylindrical one here like this, then your this side was showing that negative side is on this side here, positive on this side. This is the arrow for negative. So negative on this side, positive on this side here, right? So your resistor we used before is not dependent on frequency, but your capacitance, value of the capacitance depends on frequency. What I meant by here, your C is your capacitance, right? C is capacitance, but that is not your capacitive impedance compared to R. So R for resistance is basically equivalent to XC, which is capacitive impedance. So this is called impedance. How much impedance a capacitance has. So that impedance depends on your frequency. J is imaginary number, which is basically I if you know imaginary number. So J here is, we use J for the circuit because I is the current, J is square root of -1. So that is your capacitive impedance, and that is 1 over J, what is omega is 2 pi FC. So F is your frequency, right? So that's why I'm saying that capacitive impedance is frequency dependent, right? So that means if you look at here, if your frequency goes really, really high, your impedance goes really, really low. So that means XC goes down when your frequency goes up, right? For the high frequency signal, your capacitive impedance would be close to 0, right? And for DC signal, over here, your F is 0. So if F is 0, I'm going to bring it over here, F is 0, then XC goes to infinity, right? So that means for DC signal, your XC goes to infinity. That means it's almost open circuit, right? So for DC signal, here's the thing. For DC signal, your capacitance acts like an open circuit, and for high frequency, your capacitor act like a short circuit. So DC signal capacitor is open circuit, and for high frequency signal right here, that is acts like short circuit or just no wire. All right, so that's all for capacitor, how they behave for different extreme condition. So capacitor, as it's frequency dependent and it stores energy, it cannot change instantaneous. Let's take it over here. So capacitor, when you charge it, it charged when you discharge it, is discharged, but not instantaneously. It takes time to charge, it takes time to discharge. That means when you have, let's say, 12 volts here, this capacitor will be also 12 volts, as I said in the previous slide. So that it will take time to charge it, and it also take time to discharge it. That means you cannot make 0 to 12 volts instantaneously or 12 volts to 0 instantaneously. So if we're supplying electric load over here, that means if we have a capacitor across the electric load, that will say that this will that will supply, even though it might change input, but output would be always close to 12 volts. That means it acts like a shock absorber in your car. In your car, if you have a shock absorber, if you are driving to a bumpy road, the shock absorber absorb the shock. Here, your capacitor will absorb the voltage changes, right? And then your load will not feel that much change. It will feel a little bit, but will not feel that much. Let's say if you have this voltage over here, let's say it's an average 12 volts, but it has some kind of bumpy road here, it's 12 volts, and over here that will feel maybe a little bit bumpy, but very close to 12 volts. That's what this capacitor does. It basically supplies constant voltage to the load. That's why all the power electronics power conditioning circuits has capacitor in the input and capacitor in the output to basically take out the voltage fluctuation for the load. And also, you know that for DC circuit is an open open circuit. So if you have a DC signal coming here, that cannot travel through the capacitor, so your load would not feel any DC voltage. Let's say you have a voltage over here, it has a DC voltage and also has a AC signals. So this offset here, let's say, is 2 volts, and this one is peak to peak is 1 volts here and 1 volts here, so 2 volts peak to peak. So this is the input here, right? And output, your DC cannot travel to the capacitor, so your output will be just like this. So 1 volts here and negative 1 volts here. Can you see that? So your DC volts would be filtered out by the capacitor, because the capacitor cannot allow DC volts to go through it. And over here, also can eliminate the high frequency. In high frequency, your capacitor acts like a short circuit, right? So if you have a signal coming here that has all kinds of frequency, high frequency, low frequency coming here, so that it has different signals and different frequencies, right? But you only want the low frequency output. So at the output, what will happen over here, you your frequency, let's say it's your frequency here, so you only have the low frequency coming in and all the high frequency will be blocked. So this is the signal over here, V out. You only have the low frequency going through it and high frequency will be blocked, because high frequency would be short circuited through this capacitor. So that is as a filter for the frequency. So that means your capacitor could be used as a DC block, as a shock absorber, and also could be a filter for the circuit. And you can also make active filter by using active device like op-amp. Here you learn them in your ECE310 or ECE280. That's what we discussed, op-amp and how to make circuit about it. So that's all for the capacitor. I'll see you in the lab. I will have an interesting lab on capacitor. We'll learn more about the capacitor during the lab. All right.